Hello everyone. So welcome to the second installment of Sigma Steel Academy for Flexural. So this video will basically be supplementary to the previous episode. So it's basically assuming that you've already seen the previous one. My thing's lagging. We're recording this pretty early in the morning, so forgive me if my voice sounds really raspy and my brain's really slow. So pretty much, just to give you an idea of where we're at, I've released, this will be my fourth video on Flexural. So there'll be I'll give you a recap of what all these videos are about. Basically, the first Flexure video, I didn't really cover anything too technical. In fact, it's just kind of a live recording of me yapping. But this was designed to basically teach you about load paths, beams generally, what's the purpose of steel beams, how do they manifest in real life, and a little bit on connection design. Very little bit. We'll talk about that more when we're talking about actual connections, but kind of just getting you to think about what does a beam look like in real life? How does one beam connect to another beam in a realistic setting? And I also, in that video, introduced the concept of lateral torsional buckling through physical demonstration. So if you haven't seen that, we'd highly recommend you check out at least that portion of the video, because that's a very important concept. Okay, in the second video that I released, it was recorded by Farhan, so I'll just be referring to this as Farhan's Yap, where he covered a previous year's assignment where he was determining the section capacity for a monosymmetric I-beam, aka an I-beam with unequal flanges. So monosymmetric being it's symmetrical about only one axis. And he was asked to find MS, which is a section capacity. In that video, he also covers a little bit on MB, which is the overall beam capacity. So that's including lateral torsional buckling components and stuff like that too. A monosymmetric I-beam is a very specific type of custom section. Okay, and it has very unique kind of properties. You have to look in the appendix to find, how to find J, the torsional constant, and the warping constant, and stuff like that. And MO has a very specific formula for monosymmetric I-beams. It's actually not a very usual scenario that you run into in real life. So that brings me to these videos, right? The Sigma Academy videos. So you don't really have had to have watched these videos, to be honest, in order to enjoy the Sigma Academy videos. Flexure, I kind of realized when I was making this video that these previous videos didn't really thoroughly cover the concept of how do we calculate MS and MB. So that's what this video, that first video in this series, was designed to do. To kind of introduce you to the idea of how do we actually calculate these values that we're looking for, for ultimate beam design. And specifically in that video, we covered a standard section. In other words, you can look on one steel and you can find a specific, universal beam, for example. And then what's the section capacity of that? In order to find the beam capacity, you're actually given some information about, the loading conditions and what your beam's geometry looks like. I don't remember exactly what it was in that video, but you need all that, and you need the restraints. Those like lateral restraints and stuff like that in the video in order to work out the beam capacity. So in this video, the idea is that we're going to go through another custom section, so similar to Farhan's video, except instead of a monosymmetric section, I'm going to go through with you and explain how a box section works, right? A custom box section. The thing is about this box section, which looks like this, is you might be wondering, Okay, this is a rectangular hollow section, and I guess by like literal definition, it is kind of a rectangular hollow section. Like it looks, hollow and it's rectangular and it's a section, right? So by like a literal definition, it kind of fits that. But a rectangular hollow section implies that your section's cold rolled, okay? And that would mean that it has like a certain. It's a standard section basically, like these RHSs. It implies that it's a standard section with a certain, for example, fillet radius on the corners and a certain, gauge or the thickness of the steel. And these are always cold formed. And on one steel, you might see that. Sorry, if you Google one steel, right, on Google, the first thing you're going to find is the hot rolled sections. Okay, and that's all your universal beams, PFCs, etc. Any kind of open section. But if you search one steel cold form or one steel hollow section, maybe if you Google that instead, you're gonna find a bunch of RHSs and SHSs, like square hollow sections, circular hollow sections, etc. And that's different to what we have today. Okay, because we have a box section. I'll just call it a hollow box section. But we custom made it ourselves, okay? And when you custom make it yourself, it's not cold formed, because cold form would imply that a machine just shits it out basically, and it's like formed into this, like when it's cooled down basically, for cold formed. So yeah, basically, what am I trying to say? So basically, we have individual plates, right, that make up our box section, and then it is heavily welded, okay? So heavily welded means, for example, they might do a full penetration butt weld. It doesn't really tell you how it's connected, but this is like the implication, right? In the shop, they go through with many passes to make sure that this box section is completely rigidly connected. So that's basically heavily welded. Okay, so it's a little bit different in how it's made. Okay, so that's important for one of the steps where we talk about like the manufacturing of the steel, like section. Okay, that was a bit of a rant. Let's get to the actual question. So for a beam with a built-up box section, shown in this figure right here, calculate MS, MB, and it also asks us for shear, but we're not going to do that today. We'll cover shear in week 7 and onwards. Okay, it shows us the shear force diagram of the beam. I think this is a previous assignment question, by the way. I think this is how I have it. Yep, and then steel plates are grade 300, heavily welded, ignore self-weight of the beam. We have the restraints shown on the diagram itself. Beam has no out-of-plane rotational restraint, so that's just referring to when we get up to KR in the calculation of effective length. Both spans AB and BC have lateral restraints L 3 meters away from B, etc. You're required to make any assumptions because of missing information. Please state any assumptions that you made. Okay. So, basically we have a continuous beam, right? We have 2-span continuous beam. That's one span, that's another span. And it's symmetrical, okay? That's the first thing you gotta realize. We're given just the shear force diagram, but from the shear force diagram, we can kind of like back work a bit of information. So on a shear force diagram, whenever you have a discontinuity or a jump, that can be from a point load or a reaction, okay? So in this case, let's call this AY, which is the vertical reaction at A. And we know that's equal to 120. And then at this support, BY, we know that BY is equal to 400 because it jumps from negative 200 to positive 200. and we know that cy is also 120. And you can see that we have, equal distances, and basically we have like a symmetrical loading condition. So about the middle, everything on the left is just a mirror of everything on the right. We also have this linear load, I guess, uniformly distributed load on it, which causes the shear force to gradually fall at the same rate. We actually don't really care what that is. We just care about trying to derive the moment, okay? And the way that we do that is we need to basically find the area of these triangles, okay? And since it's a mirror, we just need triangle 1, we need triangle 2. If we find the area of these, we can find the bending moment, okay? But what you'll find is that the first thing we need to know is this distance, which we'll call x. Like, we don't know what this distance is of this triangle. We know that the entire length is 8 meters, okay? But the way that we work this out is we use similar triangles, okay? So we say that this slope of the first triangle is equal to the slope of the second triangle, okay? So on the left, we'll say the slope is equal to the slope of this one, right? And how do we calculate slope? We go rise over run is equal to rise over run. So the rise of that first triangle is 120, and the run is x. And the rise of the second triangle in absolute value is 200, and the run is 8 minus x, right? It's 8 minus x, okay? Next we cross multiply. And I can't be bothered to do the maths, just give me a sec. Yeah, basically once we expand this out and rearrange a bit, we find that x is equal to 3 meters, okay? So, cool. Basically, that means that this distance here is 3 meters, and therefore this distance here has to be 8 minus 3, which is 5 meters, okay? So now we know the base dimension and the height of these triangles, okay? So we can work out the area, okay? So area of a triangle, half base times height. Half the base is 3 meters, the height is 120, and then negative for the second triangle, half the base is 5 meters and the height is 200, okay? Cool. So this gives us 180. We're multiplying kilonewtons by meters. Oh, sorry, other way around. Meters by kilonewtons. So it's going to be in kilonewton meters. And second triangle is negative 500. So at this point here, when we've traveled 3 meters, we know that the entire area of this triangle has been covered. So that's 180 kilonewton meters. After another 3 meters, it goes actually back down to 0, but we don't really care about that. It's just because if we travel another 3 meters, we've basically done the same triangle, but one's positive, one's negative. And then when you add them together, it gives you 0. But up here is the more important point. It's where you add the entire thing. And that's basically saying 1 plus 2, which is 180 minus 500, which gives you negative 320. Okay, so this is our critical maximum bending moment, right? Cool. So let's move on from the bending moment to steel properties for a custom section. So let's just look at the dimensions themselves, right? This is our box section. Whenever you have a section, you want to think about what are the areas which are, whenever you have a custom section, right? So when you have a standard section, you don't have to think about any of this because one steel will give it to you, right? One steel gives you this magical number, or all of these magical numbers basically. But if it's a custom section, you have to work out the sectional properties yourself. And ZE is a pain in the ass because it requires you to do all these further steps, okay? So the first thing you want to do when you're working on a custom section is you want to realize that whenever you have, how do I say it? Okay, so another example would be a I-shaped section made up of different plates, right? Basically, whenever plates intersect, right, you have these areas which are imbuckleable, okay? And then if you're thinking about compression forces going into the page, you essentially have this cantilever beam. Let's just say this is looking like that, okay? So in and out of the page, you have this force, and it's causing the cantilever to bend like that. So in this case, this flange of this I-shaped section is supported on one side. Okay. Yeah, it's only supported on this side, and this is the non-buckleable section. For the web of your I-shaped section, you basically have this going on. We have double fixed support, and say there's a compression force happening at the middle. Just, I know it's not quite what's happening, but just for example, you basically have these two supports which are stopping buckling from happening. So you're supported on two sides, right? Okay, back to our section. We actually have supports on both sides for both element 1 and 2, right? So I've grouped the similar elements together, but these unbuckleable sections act as fixed supports, you can think of it as, and then it's like, yeah. Anyway, the notation T and B, B refers to the larger dimension and T refers to the smaller dimension, okay? So for element 1, for example, we have a width going left to right, and we have a thickness going up and down, right? And it just depends on the orientation of your element, because for element 2, you can see it's the other way around. So width doesn't necessarily refer to like left or right. It can be up or down. It's just the larger dimension, and the thickness T is the smaller dimension, okay? Yeah, so I've basically just written out what these values are. And the thickness, remember, thickness is always the smaller dimension. And that's going to be important for when you're determining yield stress and stuff like that. And the order which you're writing your effective slenderness. Or element slenderness, or whatever, okay? Okay, so let's start with yield stress, okay? So in the standards and also in my notes, for grade 300, which is determined using this standard, you basically, you go to the part which says plates, and you look at the steel grade and find the corresponding thickness, right? Since we have thickness of 8 for all our elements, right, we're in this range, and in this range, yield stress is 320, okay? So that's pretty straightforward. So we just find that we're going to use 320 for the yield stress. Next is the Z, like we're trying to find ZE now, okay? And this requires a few steps. The first one is finding what's the governing element, right? So you know how we have two different unique elements, right? We have 1 and we have 2. So which one's going to govern in terms of our overall section before it starts to locally buckle, okay? Now, I know we talked about this a little bit during the compression topic. We talked about the idea of local buckling, and it's very similar for flexural buckling, right? But I'll tell you, like, local flexural buckling, but I'll kind of explain that a bit more as we go, okay? Let's just plug in some numbers for now. Okay, so the width of the first element was 230. Remember, our first element, I believe it was the horizontal one, right? Yeah. So basically, if this is our box, we're not counting these areas here. B1 was there. T1 was here, okay? And that was 230 for width and 8 for thickness, okay? And for our second element, B2 was this, T2 was here, okay? So that's 308, okay? Once we plug it into this formula, we get these values, right? So this is our element slenderness. So you can kind of see this makes sense because B2 is more slender, because if you we just put them in the same orientation, right? B2 looks like that, B1 looks like that, right? B1, same thickness, but it's a bit shorter, so it's a bit stubbier. So therefore, you know, maybe like less likely to buckle, but that's not the only thing that determines our slenderness in the case of flexure, because we have to consider slenderness limit, okay? So what do I mean by this? The idea is if our section is bending about this neutral axis, right? It doesn't work quite like compression, because in compression, right, you can imagine compression, so just pretend this section's in compression. The entire thing is experiencing some compression force in the previous topic when we were determining this. And so everything's in uniform compression. But in this topic, it actually works differently, because if we're bending about this axis, right? If we have a beam, right? Different parts are going to experience different amounts of compression and tension. So element 1, I'm going to highlight this. Element 1, I'll highlight in blue, is going to experience what we call uniform compression. So the whole thing is going to be experiencing compression all at once, right? Due to our flexural like stress distribution, right? Element 2, which I'll do in red, actually not all of it's going to be in compression at once, okay? Because only this part is going to be in compression like at a time. So parts of it are going to be in tension and parts of it are going to be in compression. So even though it's more slender technically, right? Like, you know how we're talking about the second element, feels like it's going to be like more likely to buckle. The actual stress that it experiences is going to be partially tension and partially compression. Now you might be wondering, why the hell are we considering element 1, for example, at the bottom if it's in tension, right? And why is this described as only like uniform compression? It's because if you think of the bending moment diagram of our loading situation, and just like this is generally speaking, okay? So that's our beam, and the bending moment diagram, remember, looked like this or something, right? So in areas of positive moment and negative moment, we actually have different behavior of our stress distribution, right? So our stress distribution, where there is positive moment, we'll basically have compression at the top flange and tension at the bottom flange, okay? And this is true on both sides of our beam. But once we get to the area of negative bending moment, our stress distribution actually flips, right? So we get tension on the top side, compression on the bottom side. So in this case here, the bottom is actually going to be in compression, okay? But it doesn't really matter. The idea is the element 1 and 2, regardless of which one's in compression at once, like we just treat it as the same thing. So it's just when it's in compression, that's the worst case scenario. So we're going to take it like that. But the point is, for element 2, whether your stress distribution looks like this or the other way around, one side's going to be in compression, one side's going to be in tension, okay? At any given time. So, with that said, for element 1, which is always in uniform compression, I know it's a trapezoid, but it's like, this is close enough to being like uniform that we can consider it as uniform compression. And it has both edges supported, which just means that it's a fixed support on both sides. and it's heavily welded. So this is to do with the manufacturing process. We said that, it's heavily welded, right? Gives us a certain number, which I'll show you below. And element 2, why does it say 1 is supported? That's wrong. It should be both. So there should be both edges supported. Yeah, I just read the wrong thing there, but I took the right value down here. Compression at one edge, tension at the other, okay? That's heavily welded. So basically, we're looking at this table. We see that both edges are supported, and here we have uniform compression, here we have compression at one edge, tension at the other. So this represents our element 1, this represents our element 2, okay? So we go over to this row. Oh, sorry, yeah, heavily welded, or any. That's a bad color to do. So, and we find 35 and 115. So this one's 35 is the slenderness limit, and 115. Okay, so you might be thinking about these numbers, and they're pretty different, like 35 versus 115. We know that the slenderness, when it's higher, is worse, right? But for a limit, it's a bit of a different story. So element 1, yeah, element 1, element 2, okay? Think of it like a health bar, okay? So for element 1, our HP is 35, right? So that's our yield limit. And element 2, the health bar is way bigger. I'm not really drawing this very well to scale. Let me try that again. The HP is 115, okay? Element 1's actual slenderness is 32.53. So this is the slenderness, right? Let's think of this like damage. Slenderness. And that was, what was it? 32.53. Okay, and then for element 2, 42 point, whatever. Let's do 42, okay? So essentially, what you want to look at is the damage to HP ratio, okay? And you can tell that the first one's is like pretty close to its yield limit, right? The first one, the slenderness to yield limit ratio, is worse because when it's higher, it's more governing, okay? Like 2 can handle more because of the parts of it, like only parts of it are in compression, parts of it are in tension. Anyway, hopefully that makes sense. So that's what we're calculating here. This is your damage to HP ratio. That's the analogy I'm going to go with. And I'm just going to chuck it in to these. And we find this one is 0.93. So there's a 93% utilization, I guess you can call it. Whereas this one is way lower. So this is a lower utilization, so it's not close to its limit at all. And whichever one is closer to its max utilization is going to be our governing section, okay? Now, I'm pretty sure this can be over 1 as well. So if the damage is like over the HP, quote unquote, it's pretty bad. And that would be the governing one, right? Okay, so element 1 governs. And so I'm just gonna, because a lot of these terms look similar, I'm gonna highlight these in different colors so that you can kind of see the pattern, right? So 32.53, we're gonna take that and restate that as a new governing value. Oops. And 35 is going to be our slenderness limit. Because element 1 governs, we don't actually care about these values anymore. The other one you have to consider is your plastic slenderness limit, okay? And this isn't something that we've grabbed so far, but we go back to this table, and we go back to the row which our governing element was in, and now we go to our plasticity limit, and we find that it's 30, okay? So here's where the HP analogy falls short a little bit. We have to kind of think of this in terms of a new analogy, but what we're doing now is we're classifying the section's slenderness, right? So we need to know if it's compact, non-compact, or slender. So the idea is that if I draw this out, we have, how do I say this? If 0, we have our plastic limit, plasticity, and we have our yield. Okay, and for us, these values were 35, 30, and 0, whatever. Okay, and we need to know where our section slenderness falls, right? So for us, our section slenderness falls here. Okay, and there's 3 regions, right? I might do these in different colors to make sure it's obvious what's going on. Let's do red, orange, yellow. So red would be like, let's do it as bad, would be out here. Orange would be here. Yellow would be here. Okay, so yellow is if our section is compact. Orange is if our section is non-compact, and red is if we're slender. So remember, slender is the worst, so I've done it in red. Just means that you're going to lose a lot of the capacity. Compact's the best in terms of not losing as much of your, what do you call it? Capacity. Okay, what am I trying to say? And basically we fall in the orange region, which is your non-compact region, right? So all we're doing is comparing these numbers, finding which one it falls into, right? So we can classify our section as non-compact, basically. Okay, with all that done now, so we've classified our section. We know which formula we're going to need for ZEX, the calculation of ZEX, and so we're going to work towards that. We're going to figure out IX. So IX is your moment of inertia, right? And specifically bending about the XX axis, right? So major axis bending. Yeah, it's going to be bending like that way. Okay. So what we can do for a box section that's I don't know. Well, like what we can do for a box section that's like, fuck, how do I say this? Yeah, basically we have a bigger box, and then we can subtract the smaller box in terms of its BD cubed on 12. So we don't need to do any like parallel axis theorem shifting or anything like that. All we need to do, so that's the purple box, right? We just subtract that from the bigger box, right? That's the blue one there. I'll just do the hatch in the other direction so it's clearer. There we go. Hopefully that's clear as to what I'm doing mathematically, right? So doing BD cubed on 12 minus BD cubed on 12, but we're going to plug in different values. And yeah, I've just listed out the dimensions basically that we're doing. That gives us on a calculator 129.4 times 10 to the 6, and this is in millimeters to the power 4. Yep. Okay. So okay, this one requires a bit more of an explanation, but as I briefly alluded to, like in the in the previous few videos, Z is our elastic section modulus, and basically when we're calculating, how do I say this? When we're calculating our moment capacity, our section moment capacity, what we need is we need Fy times Ze. Okay, so we're trying to find Ze, which is the effective section modulus, right? But the effective section modulus is not quite the same as the elastic section modulus. What we need to find is Z, which is your elastic case, and S, which is your plastic case, right? So this one's plastic. This is elastic. And the idea is that Z can be between elastic and plastic for non-compact sections, okay? So we need to basically find both of these values, and then we're going to need to compare them in the formula, right? So for elastic section modulus, my is our yield, our first yield moment, and we can find that by using this formula. So Z is basically, if you're in elastic bending, right? So here's our box section, here's the neutral axis. Basically, this value here is Fy, okay? And the overall moment capacity is going to be the overall, what am I saying? The overall first yield moment is going to be the sum of the moments due to these forces causing the spin, right? But that's a pain in the ass to do. So you can do a formula instead, which is Fy times Z. Okay, so what is Z? Z is equal to the moment of inertia over your Y hat. Okay, and so what's Y hat? Y hat is your neutral, how do I say this? So this is depth, right? Depth is the overall depth of the section. Y hat is the distance from the outer edge to your neutral axis, okay? And regardless of which side we take, Y hat is going to be the same because we have a doubly symmetrical section, right? Now the difference is, in Farhan's video, you can see that they had a monosymmetric eye section, and just from looking at this, you can see that there's more quote-unquote meat at the bottom. So our neutral axis is skewed towards the bottom. I might exaggerate that even more. So neutral axis is skewed towards the bottom because, you know, there's more meat down there, okay? And so you have two values for Y hat. You have Y hat top and you have Y hat bottom, okay? Now, I'm actually running out of space. Okay, give me 1 sec. This is important. I'm gonna move all this over to a new page, okay? So what am I trying to do here? So I'm trying to compare two different sections. So I'm gonna put them top down from each other, okay? So the idea is with the monosymmetric section, your stress distribution looks like this, right? Because the neutral axis runs through, and that's the point where there's zero stress, right? So in bending, so basically you can see that for our first yield, our stress like scales like faster on the side that has a higher Y hat. And so in our formula for a monosymmetric section, what we do is we do Ix over Y hat max, right? Where Y hat max is the max, I guess, between Y hat top and Y hat bottom, okay? Sometimes you might see the idea of Z top and Z bottom, okay? And Z top and Z bottom is just referring to which side you're taking it from, okay? So Z top is Ix over Y hat top, Ix, and then Z bot is Ix over Y hat bottom. Do you see what I'm saying? So these will give you two different numbers, and the more critical one is the one which reaches the neutral axis faster, right? And so you'll find that in this case, right, Z top will give you a lower number, and Z bottom will give you a higher number, right? And the lower number is going to be the more critical one, right? So that's what happens for a monosymmetric section, but for a balanced doubly symmetric section, right? It doesn't matter which side you take it from, because y hat is going to be equal on top and bottom side. And so in our case, we're just going to use the formula d over 2, because y hat is just going to be right in the middle of our overall depth. Okay, so that's what's going on here. Anyway, this is like a long way of saying this is how you calculate z. So z is your elastic bending section modulus, okay? And it's in millimeters cubed. Okay, so next is plastic. You have to find S, right? And in order to find S, so that's what we're after. We have to find the plastic moment, okay? So we do this, step 1, and then we divide MP by Fy, and we get step 2, which is S, which is what we're actually after. Okay, so there's like a little bit of an explanation I included in my week 4 YAP, but I didn't really explain it properly. The idea is now, instead of a stress distribution that looks like this, right, because this is the case of first yield, we have a stress distribution that looks like this, right? Okay. So the idea is that everything is now yielded, okay? And let's just say the bottom's in compression, tops other way around, I guess. Tops in compression, bottoms in tension. And we can turn these into force blocks, right? Now, force is equal to stress times area, right? And we have different widths, right? So we have this portion, which is going to have a certain width, right? But then we also have this other portion. I'm running out of colors. Which has a different width, right? We can combine these together. Let's call the combination of these two widths B2, right? So that and that. And that's going to result in different forces, right? So here we have compression force 1 due to the first width, okay? I should say the first area, I guess, yeah. Due to the first area. So let's call it area 1. And then these two combined is area 2. Okay, so that's C1, and the orange one is C2. That's the neutral axis, right? And then going the other way, we have a similar thing going on. We have, let's call it T2 and T1. Okay, and what we want to do is we want to find the sum of the moments, right, about the neutral axis, and that will give us MP, okay? And then from that value, whatever we get, if we divide it by Fy, that's how we find our section modulus, okay? So that's what we're going to do. What have I done? Okay, so basically we're here. It doesn't really matter what Fy is because we're going to divide it out in the end. So we're going to do just the areas, right? So this is thickness times width. So this, right? Our width is 246 and our thickness is 8. Okay, so that's just the area, right? Gives us that number. And then we also know the, what do you call it? From the neutral axis, the dimension to the middle of this element, from here to here is 154, right? Because what we've done is 150 plus half of 8. Okay. And next we have this one. And so that is your, it's basically this. That's 150, right? That's 8. Okay, so that's the area 2, right? Area 2 gives us 2400, and we have a mirrored effect on the other side. Okay, so what we want to do is we have 2 lots because we have a mirrored effect. So I'll do yellow. 1, 2 lots of this, and then I'll do green. 1, 2 lots of this, and we're multiplying by the lever arm from the neutral axis of these forces, right? That's how you calculate area, right? We're doing force, right, which is your stress times area, and the lever arm. Sorry, we're doing 2 lots of them. Anyway, yeah, it gives us MP as that. Since we're actually looking for S, we can just divide out Fy. So we can find that S is equal to simply this number, basically 966,144. But what we're going to do is we're going to word it slightly differently. We'll just do it in terms of 10 to the 3 millimeters cubed. Anyway, that's our value for plastic section modulus. Okay, now we have a specific formula for non-compact sections, right? And the idea is that, how do I say this? Okay, the idea is that for compact sections, non-compact sections, and slender sections, okay, we have 3 different formulas, right? Compact one, okay, so basically slender, non-compact, and compact have different ways of calculating ZE, okay? So for non-compact, ZE can sit in this region, right? For slender, ZE can sit in this region. And for compact, ZE can sit in this region. Okay. So we need both Z and S because it's going to be a function of both Z and S, right? For slender sections, you actually don't need to calculate S because you'll never reach S, basically. So I might explain compact and slender first, and then I'll explain the one for our example NC, right? So compact, basically ZE is the minimum between S and 1.5Z. Okay, so it's either S, the minimum between S and 1.5Z. Sorry. Okay, so compact can't sit here. The thing ends here, right? Compact can be here to 1.5Z, okay? Right, so if 1.5Z is lower than S, right, it's whichever one's the minimum. Okay, now I'll explain slender. So circular hollow sections have their own formula, which I won't explain at the moment. Section made up of flat plates. It depends on which one is the governing element, right? So for example, we determined that our box section, just pretend it was slender for a second, right? We determined that our box section had 2 elements, right? One which is in uniform compression, and the second one which had tension and compression, right? And so basically the second one is saying if the section is governed by element 2, in our case, use this formula. Otherwise, if the section is governed by element 1, in our case, use this formula. Okay? Yeah, so that brings me to non-compact. So for non-compact, your effective section modulus is all this shit, basically. So this one's the most complicated, and it requires you to calculate what the effective section modulus was for compact first, right? So ZC is what is the effective section modulus as if your section was compact to begin with, right? And so anyway, that's what we're doing. Cool. That's that. Okay, so hopefully that explains somewhat what's going on. Give me 1 sec. Let's go into my notes again. Okay. So anyway, the values for S, right, was 966.1 times 10 to the 3, and 1.5 times Z was just whatever value we had for Z, and then multiplied by 1.5. And the minimum is just S, right? So we're sitting, oh man, I'm running out of colors. We're sitting here, okay? Because 1.5Z brought us out here, and so we're doing the minimum. It's just this one. So that is basically what the compact section modulus would be. Compact effective section modulus, right? And that goes into here. Now we're doing the entire thing. So Z was this, we plug that in. This has basically just become S, right? So S goes into here, Z goes back into here. Now, these were all the values that we found for our section's yield and plasticity limits and the overall section slenderness, right? So that gives us this value here. In terms of our timeline, that sits somewhere in between here, right? So remember, S was 966.1 times 10 to the 3. Z was 818 times 10 to the 3, right? We have a value that's in between, right? We have a value for ZE that's 891.7 times 10 to the 3, okay? So we were just finding something in between that. That gives us ZEX, okay? So next, that finally gives us ZEX. Now we can find the moment of inertia about IY, which is basically bending left to right now. This is important because when we're calculating lateral torsional buckling, it's about how likely is our section to buckle left to right. Lateral buckling, right? So we need this value. We're going to do the same thing. We're going to do big rectangle minus small rectangle, except now we're going to do B cubed and rather than D. So this is going to give us our minor axis stiffness, right? Flexural stiffness. Okay, so it gives us that value. Next is a torsional coefficient. So the question actually gives you the torsional coefficient calculation for a box section. This is it's basically different. Like finding the torsional coefficient is basically different for every unique type of section, and this just happens to be for a box section, right? You don't have to memorize these. This will be either given to you as a formula directly, or they'll just give you the J value because there's like a bazillion different combinations. It's not something that you're expected to memorize, right? So anyway, we plug in all these things for J, all these values, right? And we find J is equal to this. Okay, so that's our torsional coefficient. Next is our MS, so our section capacity. So you know how for our standard section, it was actually very easy to get here, right? Because we just go to one steel, you find these values, and happy days. But this was the thing that took us fucking a million years to find out. Once you divide that by 10 to the 6, right, to get from Newton millimeters to kilonewton meters, we find that is 285.3. Now we're going to divide our beam into segments and subsegments. I'm going to skim over this relatively quickly because the majority of the theory regarding lateral torsional buckling was covered by my previous Sigma Steel Academy video. So this is more going to be outlining any differences there is between that video and this video, right? Moment amp factor, we're going to use this formula from the table. And specifically, we know the bending moment here. If you recall, our beam looked like this. And this value, I believe it was 380, right? Off the top of my head. Oh, sorry, it was 320. So we plug in negative 320 for alping. I mean, up to you. You can do negative 320, or you can have the distributed load be positive. Sorry, that's something I should have mentioned before. Basically, we did kind of have to figure out what the distributed load was in order to use that bit of the table. So this distributed load, how do you find this? We find that our shear force goes from 120 down to negative 200 over 8 meters. Right, and so that total difference is 320 over 8 meters, which gives us 40 kilonewton meters, right? So that is our distributed load, basically. Sorry, kilonewtons per meter. And that's what goes into here. Otherwise, you just follow the formula. The steps are basically the moment here is equal to the formula that I give you. Rearrange for beta m. Once you find beta m, make sure it's within the range. Otherwise, you can reset it to be within the range, and then that's how you find alpha m. You need you basically do this formula and find alpha m that way. And alpha m is 2.25, right? Cool. Yeah, effective length. This is pretty similar to last video, so I won't cover it too much. The only thing was for our beam. Sorry. Basically, this was 8 meters, right? And we have restraints here and here, partial or full restraints. I can't remember the order. It said there's a lateral restraint here, 3 meters in, which means this is 5 meters. Right, so if you're wondering where that 5,000 comes from, we're taking the subsegment right now from A to D. Okay. We're going to assume top flange loading. It's an assumption that isn't stated in the question, but it's more conservative than shear center loading, and it's actually pretty common in industry to assume top flange loading when you're unsure. Yeah, so 1.4 is a very common number that you're going to see for KL. Yep, happy days, cool. Subsegment D to B, which is from here to here. Basically, in this portion of the table, when we have P to L, right? So basically, this was fully restrained. This was partially restrained. When we go from L to P rather than F to L, right? So subsegment D to B, we have to follow this formula, which basically is talking about, this is the number of webs, D1, TF, TW. I'll just show you on here. D1 is from the clear depth, is basically the clear depth. Thickness of the web, thickness of the flange. There's 2 webs because we have 2 walls for our rectangular hollow section. It gives us this number. It's actually not a big deal. I'm not gonna lie. I've never bothered using this formula for any of my calculations in real life. I just take it as 1. But it's gonna give you a few extra millimeters in our overall length, right? For effective length. Okay, so not the biggest problem if you don't consider this, to be honest. Okay. And basically in our question we said, assume there's no out of plane rotational restraint, which is talking about this value. Oops. Too far. Talking about this value here. All right, if you look at the table, we have we followed the non-restraints, right? Okay, you multiply everything together, you find this is our effective length. So this is from A to D, this is from D to B. Okay, so we're comparing these two. Yeah, reference buckling moment. This is specifically the formula for a box section. So you'll notice it's different to the previous video. it doesn't have the warping constant. Basically, we don't need to work out the warping constant for box sections, right? Because it's not in the reference buckling moment formula. Yeah, and so once we plug in LE, which is the only part that's different between the subsegments, we find these two values, okay? Slenderness, reduction factor, yeah, we just plug these ones in, right? And then we get two different slenderness values, right? So essentially, if you think about it, right, this is our beam arrangement. Okay, and it continues. The idea is that alpha M is calculated for each segment. So a segment is from a full restraint to a full or partial restraint, or whatever, from like full/partial restraints to another one. That's a segment, right? For a segment, we calculate alpha M. For a subsegment, which is like from here to here, we calculate alpha S, right? So we want to compare the worst combination of alpha S and alpha M. So you have to multiply these two together. You got to find the worst one, right? But it doesn't end up mattering because these two values, right, alpha M times alpha S, it can't be greater than 1 regardless. Like you'll see in the next step. And the best way to think about this is because for alpha S and for MS and MB, think of it like some dude's working at Macca's, right? And he gets, let's just say, $20,000, right? Like gross earnings from working at Macca's, part-time probably, hopefully. That's the equivalent of MS, and you have to reduce it by some amount, and that's your tax, right? But it can't be greater than, so this is your net earnings, right? But it can't be greater than your gross earnings, basically, right? So that's what's happening here. You can't have these two be greater than 1 because the sum, the product of these two can't increase your MB compared to your MS, right? So your net earnings compared to your gross earnings in that analogy. Since MB cannot be greater than MS, we set this back down to MS. And then we do a check. Okay, does our max moment, satisfy, basically. Now, the thing is, if I was designing this in real life, right, and we find that the bending moment diagram had an M max of 320, and if my section, so if I've only done half those steps, and I find out the section is already less than 320, or 5 times the section is less than 320, I'm going to make this a stronger section. Like I'm not going to calculate MB because it's never going to satisfy our bending moment to begin with, right? You should increase your section to the point where it satisfies the overall bending moment before touching it. Do you know what I'm saying? So like, for example, if your landlord is going to charge you $30,000 a year for rent, and your gross earnings is only $20,000 a year, you're not going to be able to survive. You know what I'm saying? Regardless of net earnings. Okay, hopefully that makes sense. I'm going to end the video here. Hope you enjoyed.